solid-state batteries. Are they the answer we seek? Our lives run on electricity, and new variable methods of generation such as wind and solar require advances in electrical storage. In her latest book, The Grid, The Fraying Wires Between Americans and the Energy Future, author Gretchen Bart says that any conversation about electrical storage is 85% about batteries and 15% weird ideas. Lithium-ion batteries are a great mix of accessible and affordable materials, can be light, and are known to release stored power steadily. But the technology that currently powers electric cars, portable electronics, and aerospace applications suffers several limitations. They have limited storage capacity, flammable electrolytes, and come with the injustice of cobalt mining. Better battery technology is necessary to power the innovations of the future. The possible solution: batteries that use solid electrolytes, called solid-state batteries, versus liquid electrolytes, the most popular being lithium-ion, are a potential alternative battery technology. These solid-state batteries are expected to have a higher energy density, faster charging, higher voltage, and longer life cycle. Our mission is to follow the research teams trying to develop this solid-state battery technology and try, through research and experimentation, to contribute to their work. It is well known that lithium-ion batteries are overdue for replacement, and potential alternatives that are believed to be many years away are projected to outperform current battery technology by a substantial amount. First, some basics. NeoScribe, can you please explain a lithium-ion battery?
Lithium-ion batteries have four main parts. First is the positive electrode, called a cathode, made out of lithium metal oxide. Second is the negative electrode, called an anode, made out of graphite. Third are electrolytes, composed of salts, solvents, and additives, serving as the conductive medium for ions to pass through. Think of Gatorade, except Gatorade has water as a solvent and sodium chloride as a salt, compared to dimethoxyethane as a solvent and lithium hexafluorophosphate as a salt. We will zero in on electrolytes a little deeper in a moment. Okay, back to the battery. The fourth main part is the separator, which prevents a short circuit. So, when a battery is charging, lithium ions are released from the cathode, pass through the separator to the anode, where they are stored until the battery is charged. And as the battery is being discharged, the lithium ions are released from the anode and flow back to the cathode. And during both charge and discharge phases, electrons pass through the electrical circuit, powering the device or charging the battery. But the key part we're going to focus on are the electrolytes. The electrolytes in lithium-ion batteries are either in liquid form or polymer form, which has the consistency of gel. But as you might have guessed by now, electrolytes in solid-state batteries are solid.
Let's look at some examples of scientists working on solid-state battery designs. Professor Matthew McDowell is experimenting with an iron sulfide electrode and a sodium and potassium electrolyte. Dr. McDowell and his team have been using an electron microscope to watch what happens to particles of iron sulfide, the particles that make up the battery electrode, when they react to different types of ions. They are using a variety of in situ techniques such as transmission electron microscopy, X-ray diffraction, and X-ray spectroscopy methods to reveal structural, chemical, and morphological transformations in real time. His team watched as particles almost exploded when they reacted to lithium ions, but when they reacted with sodium and potassium, they were more stable. This discovery could mean that these batteries are safer, have a higher energy density, and last longer. Our second example comes from a team of MIT researchers. They recently demonstrated a method to make a smaller, safer, and faster battery. They used a new pulse laser deposition technique to make thinner lithium electrolytes. Check it out. They used a laser beam to build up a solid wafer cookie on the substrate. They alternated layers of active electrolyte lithium garnet component. They go through some more steps baking it, a process called annealing. This gives them a solid electrolyte that has faster conductivity. Super exciting. An additional example of cutting-edge battery innovation comes from a small company called C-Lab. They recently took a typical lithium-ion battery and modified the battery by replacing the graphite anode with a silicon anode. They used chemical engineering to complete the process of replacing the graphite anode with the new silicon anode. Because this new anode is made of silicone, it is more energy dense and can last longer because of its rigidity comparatively to graphite. This process would likely be useful to bridge the production gap between lithium-ion batteries and solid-state batteries, as this process simply modifies the current battery as opposed to implementing an entirely new process to accommodate an entirely new battery. While this example does not include the creation of a new solid-state battery, it certainly is a phenomenal enhancement in terms of battery technology and will likely lead to greater advancements. Stay tuned for more investigations from charging into the future. And don't forget to like our video and visit our website.